Welcome to VetMed 529A, Aquaculture and Aquatic Animal Medicine. In this topic, I am going to discuss water quality management. At the end of the topic, the student should be able to recognize the effects of important water quality parameters in pond water and cultured stocks. Learn how to use water quality instruments and interpret the recorded readings of each parameter, and determine the optimum level of water quality parameters for culturing different aquaculture species. Water quality monitoring and routine management. Water quality. It is important or necessary because it determines the success or failure of a fish cultural operation. One of the parameters that we should focus on is temperature. Temperature fluctuation should be minimal. Abrupt change by greater than or equal to 5 degrees Celsius is stressful or lethal, so care must be taken. Temperature fluctuation could have its effects or influences. First is, it affects the metabolic rate of organisms. With increasing temperature, the rate of respiration is increased, and also the dissolved oxygen consumption also increases. Next is, it affects the stability of water column, which means that there is no uniformity of temperature in the water columns. The non-uniformity of temperature in the water columns is known as the thermal stratification or layering. Example of this is warmer water is at the upper column except when temperature drops to below 4 degrees Celsius, where warmer water is at the lower column. Next is, it affects solubility of gases. Solubility of oxygen is less at high temperature compared with lower temperature. It concludes that there is an inverse relationship between gases and temperature. Next is, it influences growth of aquatic organisms. There is an ideal range of 27 to 29 degrees wherein fish growth is accelerated with high survival. It also influences spawning and hatching. At higher degree in the ideal range, spawning and hatching are hastened or accelerated. For example, in tilapias, 29 to 31 degrees. We have these factors influencing increase of heat in water, and these are dissolved substances, suspended particulate matters, and planktons. Example of these dissolved substances are gases like oxygen, carbon dioxide, hydrogen sulfide, minerals like salts of calcium, magnesium, sodium, potassium, iron, and compounds of nitrogen and phosphorus, and organic compounds such as proteins and carbohydrates. Example of suspended particulate substances are the non-living particles like minerals such as silt and clay, and organic materials such as detritus and dead organisms. Another parameter that we should focus on is salinity. It is the measure of the total concentration of all dissolved salts present in a natural body of water expressed as grams of salt per kilogram of water. It is expressed in various units or way as follows: parts per thousand and percent. There are various techniques or methods in measuring salinity. One of these is density technique. It is the least expensive, and the instrument used to measure density is hydrometer. Another one is refractive index of seawater method. It is the simplest and most rapid method. The instrument used is refractometer, which is quite expensive. It directly measures the salinity of water. Another method is the conductivity method. It is a method of high precision. And the last one is the titration method. This requires reagent solutions or chemicals and is done in the laboratory with the aid of a burette, Erlenmeyer flask, and etc. Factors that affect salinity of marine coastal water. One of the factors is rainfall. Rainfall directly and indirectly reduces salinity of coastal marine water. Another factor is freshwater runoff from rivers that greatly reduces the salinity of coastal marine water, and so culture site should not be immediately adjacent to the mouth of the river. Effects or influences of salinity. It affects solubility of oxygen. Dissolved oxygen decreases with increasing salinity and vice versa. For example, at the same temperature of 30 degrees Celsius and 0 parts per thousand salinity, dissolved oxygen is 7.6 ppm. At the temperature of 30 degrees Celsius and 10 parts per thousand salinity, dissolved oxygen is decreased to 7.1 ppm. Next is, it affects the osmoregulatory function of most aquatic vertebrates, including fish. Osmoregulation requires a significant amount of energy to maintain the fish body fluids to counteract the effect of salt concentration of the habitat that may lead to mortality. Fluctuating salinity. Especially a sudden change of at least 5 ppt, it greatly causes stress or even death of fish. Next parameter is light. Sunlight is less absorbed in aquatic system at a lower angle like 1 to 45 degrees. The relation of light absorption to application of inorganic fertilizer is that phytoplankton quickly responds to fertilization at greater absorption of light energy. Higher angles like 70 to 90 degrees achieve deeper light penetration, while lower angles scatter and reflect light. This phenomenon, observed from late March to early November in the Philippines, leads to warmer water with enhanced phytoplankton and algae production compared to colder periods. We have different functions of light. First is for the energy supply for primary productivity. Light is utilized in the production of all kinds of plants. The process involved in primary productivity is known as photosynthesis. Another function is it illuminates dark water for the aquatic animals to see their foods. Light also helps to determine the kinds and amounts of food available for fish. Light also helps us to see the coloration of the body of the aquatic animals. It also triggers and directs movements of aquatic animals. The factors affecting absorption and penetration of light in the lower zone of the aquatic system are dissolved substances, suspended solids or particulate matters, and planktons. Another parameter is turbidity. It is the degree by which transparency of water is reduced by dissolved substances, suspended solids, and plankton. The specific factors that cause turbidity are soil erosion, mining waste, sewage and sewerage effluent discharge, microbial breakdown of organic matters, and planktons. The effects of turbidity cause restricted light penetration, thereby limiting photosynthesis and the production of desirable plankton in ponds or tanks. It also causes gill damage on fishes, smothering of fish eggs and destroying of benthic organisms in ponds, phytoplankton die-off, dissolved oxygen depletion, render difficulty for fish to find food, sedimentation, and the clogging of hatchery pumps, filters, and pipelines. There are remedial measures in precipitating clay turbidity, but this only applies for small areas only, like in ponds and tanks. First is the application of gypsum. As reported, an application rate of 20 milligrams per liter of gypsum can decrease 91% of the turbidity without endangering fishes and other aquatic organisms. Next is the application of agricultural lime at the rate of 500 to 600 kilograms per hectare. This can also reduce turbidity by precipitating the suspended solids. Next is rice hay at the rate of 500 kilograms per hectare, which was found to reduce turbidity. Turbidity is measured either by the following instruments or devices. One is turbidimeter. It is expressed in ppm. Muddy waters usually contain less than 2,000 ppm, and clay turbidity in natural waters rarely exceeds 20,000 ppm. Another one is the Secadisc. This device measures the transparency of water, or the distance of visibility of the Secadisc from the water surface measures the turbidity of such water. Another one is the weighing scale. This device is used to weigh the precipitates obtained from settling down the suspended solids or particulate matters. In general, turbidities less than 2,000 ppm are acceptable for fish culture. Another important parameter is dissolved oxygen. It is the gas of greatest importance in fish culture. It is a highly critical water quality parameter in fish culture. There are different uses of dissolved oxygen in aquaculture. It is used for respiration. It helps in feed consumption, digestion, and assimilation. It maintains osmotic balance of fish. It helps in fish activities such as swimming and searching of food. And it helps in the oxidation of metabolites in the aquatic environment, such as the ammonia and hydrogen sulfide, into usable form nitrate and sulfate, respectively. There are also factors that influence oxygen production in the water, and these are light availability, magnitude of chlorophyll-bearing green plants, concentration of nutrients, and temperature. It is important to take note that low level of dissolved oxygen, which can stress fish, is due to the following conditions: cloudy weather, raining, especially prolonged raining, plankton die-offs, heavy stocking of fish, and high feeding rate or ad libitum feeding. Now, if dissolved oxygen reaches low levels, fish will show signs like not eating and acting sluggish, gasping for air at the surface or surfacing, grouped near the water inflow, slow growth, and outbreaks of disease and parasites occur. Here are the management techniques in preventing problems with dissolved oxygen depletion. It is important to monitor dissolved oxygen at critical times at dawn down to 6 a.m. Avoid overstocking, avoid overfeeding, avoid overfertilization, installing of aeration, and keeping of water circulation. Next parameter is pH. It measures the degree of acidity or basicity or alkalinity of a solution. Water with pH values of about 6.5 to 9 at daybreak are best for fish production. Natural water pH is high during the day and low at night. This fluctuation is primarily influenced by the concentration of carbon dioxide in aquatic systems. During the day, phytoplankton and other aquatic plants use up carbon dioxide for their photosynthetic activity. The pH shifts towards the alkaline scale. This loss of carbon dioxide leads to the rise in pH during the day. At night, vegetal respiration replaces photosynthesis. Carbon dioxide produced through this activity brings about the lowering of the pH. The pH shifts towards the acidic scale. Another parameter to consider is total alkalinity. This refers to an ability to accept hydrogen ions or to neutralize acid and is a direct counterpart of acidity. Total alkalinity refers to the total concentration of bases present in the water expressed as milligrams per liter or parts per million of equivalent calcium carbonate. The dissolved compounds producing alkalinity may be divided into two groups. Those producing alkalinity alone are sodium carbonate, sodium bicarbonate, potassium carbonate, and potassium bicarbonate, while those producing alkalinity and hardness are calcium carbonate, calcium bicarbonate, magnesium carbonate, and magnesium bicarbonate.
Next is we have the total hardness of water. Total hardness is a measure of the total divalent cations or ionic species with a charge of positive 2, predominantly calcium and magnesium ions, expressed as milligram per liter calcium carbonate. Do take note that the hardness-causing compounds are not identified individually. Hardness values reveal that the hardness is equivalent to that produced by the calcium carbonate. Remember, sodium and potassium compounds do not produce hardness. The carbonate and the bicarbonate salts of sodium and potassium produces alkalinity. The calcium and magnesium salts account largely to the hardness of water. We also have the term soft water, which means temporary hardness, as well as hard water, which means permanent hardness. Water with temporary hardness are called soft waters. Calcium and magnesium bicarbonates causes temporary hardness to water. The term temporary is used because upon boiling, the bicarbonates change to carbonates and part of the calcium and the magnesium are precipitated. Meanwhile, the hard water, or the water with permanent hardness, is due mainly to soluble calcium and magnesium carbonates and salts of inorganic acids. As in the total alkalinity, the desired level of hardness should fall within 20 to 300 mg per liter range. Next is the ammonia or ammonia nitrogen. Ammonia is the second gas of great importance next to oxygen in fish culture. Its significance to good fish production and fish hatchery is overwhelming. In a body of water, large or small, high ammonia levels can arise from overfeeding, protein-rich feed, or excess feed decays to liberate toxic ammonia gas, which in conjunction with the fish's excreted ammonia and with urea and other foreign waste, this may accumulate to dangerously high levels under certain conditions. Fortunately, ammonia concentrations are partially curbed or buffered by conversion to the non-toxic nitrate ion by nitrifying bacteria, which can be grown on almost any coarse medium such as rocks, oyster shells, or plastic chips that contains calcium carbonates. Additionally, ammonia is converted to non-toxic ammonia ion at pH below 8. As long as the pH is 8 or lower, ammonia levels of up to 0.5 parts per million will be safe. Next is the nitrite. Nitrites are formed from the partial oxidation of ammonia by nitrifying bacteria called Nitrosomonas under aerobic conditions or in the presence of oxygen. Nitrites may be found in waters, but usually exist in low concentrations as these are readily oxidized to nitrates. Nitrite should be maintained within the limit of 0.1 parts per million. Next is the nitrates. Nitrates are the completely oxidized state of nitrogen commonly found in water. These are formed with the presence of oxygen from nitrites by nitrifying bacteria called Nitrobacter. Nitrate nitrogen may also be present in certain body of water through the introduction of chemical fertilizers, residual waters of some industries, and agricultural waste. This compound substance should be within the limit of 100 parts per million or lower. Next is the carbon dioxide. Carbon dioxide is found to be high in natural waters as a product of respiration of aquatic plants and animals. In daytime, aquatic vegetation consumes carbon dioxide and produces oxygen during photosynthesis. We have to remember that the carbon dioxide and dissolved oxygen are inversely related. When the carbon dioxide level is low, then the DO level is high and vice versa. Carbon dioxide should be maintained at the level of 10 ppm. Another characteristic is the hydrogen sulfide. Hydrogen sulfide is a product of decomposition of sulfur compounds in sediments under anaerobic condition. This form of a gas should not exceed the limit of 0.1 parts per billion. Lastly, we have the heavy metals. In case heavy metals are present in the aquaculture system, they should be at the limits or levels lower than the presented below as follows. Next is we have the recommended ways for pond management. First is we have to regularly change at least 25 to 30% of pond water during spring tides. Next, maintain a water depth of at least 50 to 75 cm for milkfish ponds and 80 to 120 cm for shrimp, rabbit fish, and saline tilapia ponds. It is also recommended to use pump to increase pond water depth when tidal current is low. Fertilize the pond only after the last water exchange during spring tide. We also have to maintain cleanliness of the siding of dikes. Regularly check dikes and patch up the leakage and seepage. We also have to regularly check the gate screens and slab. We must observe the health condition of the stocks and take immediate action if there are signs of abnormalities and disease. Next is we have the cage or pen routine management. Data on dissolved oxygen and temperature are the most valuable factors that should be collected. The time of monitoring or collection of data should be daily and at times when they are likely to be highest and lowest, which is in the case of the dissolved oxygen, temperature, and the pH levels. Monitoring of water quality is of great importance to those cage farms which are intensively managed and which have a high production with respect to the size and nature of the site. Here we have the table 1 which shows the suitable levels of water quality variables for milkfish and shrimp culture in pond, cage, or pen. For the column 1, we have the parameters, the dissolved oxygen, the pH, salinity, temperature, turbidity, and so on. For column 2, we have the method of measurement, how the parameters are measured. For example, in the pH, we use the pH meter or the pH paper. And for temperature, we use the thermometer. For column 3, we have the suitable levels of the parameters mentioned in column 1. For example, in the temperature, the suitable level is 26 to 32 degrees Celsius. That ends our presentation. Thank you for listening.